Okay, so let's talk about colligative properties. And we will be talking about those properties in relation to non-electrolyte solutions. And then later on, in fact, at the end of the chapter or close to the end of the chapter, we'll be introducing um, what happens in the case of electrolytic solutions. All right. So first we have to define what we mean by colligative properties, right? Colligative properties are properties of solutions that depends only on the number of solute particles in the solution and not on the nature of the solute particles. All right. So basically what we're saying here is that the properties that we're going to look at are affected only by the number of particles present, number of solute particles, and not whether the particles are molecules or ions or whatever. All right. So there are four colligative properties that we're going to look at in relation to solution. And the first one that we're going to examine is vapor pressure lowering. In other words, the effect that a solute will have on the vapor pressure of the solution. And that relationship is shown here, and this is called Raolt's law, all right? So P1 is, or P10 is the vapor pressure of the pure solvent, while X1 is the mole fraction of the solvent, and P1 would be the vapor pressure of the resulting solution, right? Now, if the solution contains only one solute, then we know that the relationship between the mole fraction of one solute to the mole fraction of the solvent is given here. And therefore, if we find the differential between the vapor pressure of the pure solvent and the vapor pressure of the solution, which would be represented by delta P, then that would be equal to X2, the mole fraction of the solute, times the vapor pressure of the pure solvent. All right. So that's one relation we can derive based on what we have just learned right here. All right. Oh, by the way, I think I mentioned this before, but just in case I haven't, P1 here represents the vapor pressure of the solvent in the solution. All right. So that's the relationship between these three terms. All right. Now, if you have two components in a mixture, such as benzene and toluene, that both gives off a certain amount of non-zero vapor pressure, then we can determine what the vapor pressure is based on this diagram here for a solution, depending on the proportions of the two components, right? So let me try to explain what's happening here. Here we have the y-axis, which represents the pressure of the mixture. And here we have the x-axis, which represents the mole fraction of benzene, all right, which is one of the two components in a mixture. You'll notice that it increases from 0 on the left to 1.0 on the right, which means obviously that the mole fraction of toluene would be increasing in the other direction, because remember, the sum of the mole fractions of all the components in a mixture must be equal to 1, all right? So this dotted red line here represents the vapor pressure changes for benzene as its mole fraction increases, and this dotted red line here represents the vapor pressure of toluene as its vapor pressure increases going from right to left. And this solid red line here represents the total pressure of the benzene toluene mixture as you change the mole fraction of either benzene or toluene. So basically, the way we derive or determine what this line is simply the sum of this line and this line. So in other words, if we take 0.2 mole fraction of benzene, the vapor pressure of benzene would be about here. The vapor pressure of toluene would be about here. That means that the vapor pressure of benzene and toluene would be the sum of, this looks like about 200. This looks like about 180. So we'd get up to here, which is almost 400. All right. So that's basically the relationship between the different lines. Now, if we look at the algebra of all of this here, this is the expression for the vapor pressure of one component A. So that could be benzene. And this would be the vapor pressure of another component B, which would be, in this case, toluene, which means that the total pressure of the mixture would be PA plus PB, which means that we can plug in this value and this value where we have P and PB to get this expression right here, all right? Now, we could deal with a solution. Well, oh, before I even say what I was about to say. So we call this an ideal solution, right? An ideal solution is basically a solution where the intermolecular forces does not change when you mix the two components, right? So in other words, whatever the intermolecular forces of benzene are, and whatever the intermolecular forces of toluene are in the separate components, when you mix them, the intermolecular forces between benzene and toluene would be the same, right? And therefore, we end up with this perfect straight line, which would be the case for an ideal solution, which is what is happening in the case of benzene and toluene. However, not all solutions are ideal. There are some solutions where you have this kind of plot, and this might look a bit confusing, but I want you to pay attention to this pink line right here. You notice that it is basically above the line here, which would be normally for the ideal solution. So therefore, this is not an ideal solution represented by this PT line here, right? So we have one component PA, we have another component PB, and we have the total pressure here for both components in the mixture. So this is called a positive deviation from Raolt's law. And this happens when the force, intermolecular forces between the components in the mixture is less than the intermolecular forces of the separate components by themselves, all right? So basically what that results in is basically the vapor pressure above the liquid being more than what it should be if the solution was ideal. Now, on the other hand, you can have what is called a negative ideal from, or a negative deviation from the Raolt's law. Again, pay attention to this line right here. In this case, you see it is below the line that you would see here for an ideal solution. And this is what happens when the intermolecular forces between the mixture, between the components in the mixture is greater than the intermolecular forces between the components between the separate components, all right? So those are two possibilities when it comes to non-ideal solutions. In the case of ideal solutions, you'll simply have what we described here before. Let me just go back to it. Basically, you have this particular graph here, which shows you a straight line linear relationship between the mole fraction of one of the components and the vapor pressure of the mixture in an ideal solution. Okay, I just want to mention that all that we have discussed here applies to what you see here on the screen, which deals with what we call a fractional distillation of a mixture, which is different from this simple distillation in that we have what is known as fractionating column, which contains some inert material which provides a surface for repeated heating and cooling of vapors emerging from the distilling flask. I'm not going to go into all the details, but basically what we have just learned in terms of the vapor pressure effect or the relationship between vapor pressure and the solution concentration actually is what applies when it comes to the column, which emerges, which basically produces a pure component which will come over into the condenser and then fall into the receiving flask. I'm not going to go into much detail about that. If you want to learn more about that, you can research that yourselves. Okay, so I'm going to stop here. The next topic we're going to talk about is boiling point elevation. Until next time.